Hello, scholars. Dr. Jamie Ball, and today I'm going to talk to you about descriptive statistics. So the purpose of descriptive statistics is to summarize and organize data. It is particularly effective with large amounts of data, but in research, we always do this. It presents facts from a data set, but it doesn't make any inferences, predictions, or test for any hypotheses. It's just straight facts that we can glean from the data about it. The most common measurements are mean, median, and mode, range of scores from the lowest score to the highest score, standard deviation. So some examples include an average test score for a class, or percentages of students who passed an exam. Inferential statistics, which you'll learn more about later, the purpose is to test for differences, associations, relationships. It can make predictions or generalizations from a sample about a population. The focus is probability and hypothesis testing. So this is where probabilities come into play. And the most common methods, particularly for a dissertation, would be tests like a regression, t-tests, ANOVAs, running confidence intervals and comparing them. And some examples would be predicting future voter behavior based on survey samples, or determining if there's a difference in learning outcomes between a new teaching method and an old one. So the differences here we can see. The descriptives help us to understand patterns in the data before we draw any deeper conclusions or test for them. They can support decision-making in fields like health sciences, education, and business, and lay the groundwork for inferential analyses. A lot of times there's assumptions about the data that must be true, and we usually start here. So we have some common reasons for using descriptives and inferential statistics you can see here. So let's talk about measures of central tendency. So central tendency describes where the data tends to cluster or group in a data set. So the main three key measures are mean, median, and mode. If you remember, mean is a mathematical average, but a mean is sensitive to outliers. Median is when you order the data, is the score in the middle. And if you have two scores, because you don't have one in the exact middle, it's when we take those two middle scores, add them together, and divide them by 2. And mode is the number that shows up the most frequent. Okay, sometimes you can have more than one mode. So central tendency matters first so that we can understand large data sets. Okay, and I gave you some examples here of graphs that we could use to understand our data. We can learn a lot just from looking at the distribution of scores. Okay, let's look at the histogram here in the lower right corner. We can see that the mean scores, the most scores are between score of 85 and 90. We can see that the first score, the lowest score is 75, and the highest score is 100%. We can see that the data is relatively normal shaped, approximately normal, we call it. Not quite, but so in the box plot, we can also see our quartiles and this thick line here where the average score is. So using these kind of data sets, we can support comparisons between different groups. And these are the foundations for advanced statistical analysis. But we can learn a lot from analyzing just the distribution of scores. So here I have an example data set with students A through J and their test score. And then we give the calculations mean, median, and mode. Okay? So now let's talk about measures of dispersion. This is variability. Okay? Now, dispersion matters because it describes how spread out the data is. It can help us determine the consistency in data sets, and it's essential for us to understand the reliability of an average. Remember, reliability is when you get approximately the same results or the same score over and over again. And here we have a box plot. This one's just laying on its side. And we can see our quartiles. Here's the first quartile from minimum to the beginning of quartile 2. Our interquartile range is the box itself, and our maximum is above quartile 3. Okay, it's just another way to look at it in a picture. So some of the key measures of dispersion include range, the minimum to maximum value. This doesn't give us anything to know about the shape of the data, though. We have our interquartile range, which I just showed you on the box plot, which is the spread of the middle 50%. This can be useful for helping us find outliers, things way far outside of the rest of the data. We can use standard deviation. That's the average distance from the mean, and we use it usually in normal distributions. And variance, and which is variance is the square root of the standard deviation, and it gives us the variability in squared units. Okay, so variance is a measure of how the data points differ from the mean. So if we know what the mean score is, we can look at the variance and see how far a set of data or a particular score or whatever is from the mean average score. So variance means to find the expected difference of deviation from the actual value. Therefore, variance depends on standard deviation of the given data set, so we need to know both. The more the value of variance, the data is more scattered from its mean. And if the value of the variance is low or minimum, then it is less scattered from the mean. Okay, so let me show you what I'm talking about here. I have two groups of students, Group A and Group B. You can see them here. You can see their scores. Both groups have the average score of 80, but the variance is much bigger for Group A than it is for Group B, because Group A's scores range from 65 to 100 with an average score of 80, but Group B's score range from 77 to 84 with an average score of 80. So that's what we're talking about, variance. Okay? How big is the spread? So let's talk about normal distribution and skewness. So here's a picture of a bell curve with the density line over top of it. A bell curve is symmetrical in shape with most of the values clustered around the mean. Mean, median, and mode are equal in a perfect normal distribution. They're the same number. And we use these in real world scenarios like understanding IQ scores. When we talk about the population of the United States, we would expect to see a bell curve. It can also tell us the heights and the standardized test results. It just helps us in applicability. The standard deviation determines the spread. So that's, part of the variance. It's important for probability calculations. So let's look at standard deviations. Let's look at skewed distributions first. So here I have a negative or left skew, and then I have a positive or right skew distribution. The skew goes the direction of the long tail. Okay? And the effects on the mean, median, right? If it's a right skew, the mean is greater than the median. If it's a left skew, the mean is less than the median. And you can see it in the picture. Okay. So here's some interpretation guidelines if you actually generate a statistical number from your descriptives. And we'll see an example of that data set at the end from the same student group I gave you. So a positive number above 0.05 is considered a positive skew or a right skew. A negative number indicates a negative skew or a left skew. So if our skewness, is between minus 0.5 to 0.5, there's little to no skew. It's fairly symmetrical. If it's minus 1 to minus 0.5, it's moderate skew, negative, or 0.5 to 1, it's moderate skew, positive, and beyond plus or minus 1, either direction, is a strong skew. So for example, if your test score data set had a skewness of 0.7, it suggests a slight positive skew or a right skew. And that means more of the students scored lower than average, but a few high scores pulled the mean upward. So now let's talk about kurtosis, peaked versus flat distribution. So kurtosis describes the shape of a distribution's tails. How thin or thick are they? How tall and spiky is your data distribution, or flat is it? It helps us assess whether a data set has extreme outliers or is more evenly spread. Okay, this works with skewness to understand our distribution. So here are our types. There's mesokurtic, which is normal, balanced tails. Leptokurtic is very peaked, very pointy, high, tall, narrow distribution. And platykurtic is low, that's relatively flat and wide. And I have a picture of it right here, so you can see what those mean. All right. Now, in traditional statistics, we would look for 3. But in JASP, instead of 3, it hovers around 0. And all of you will be taught in JASP. So bear that in mind. Interpretation guidelines for the actual calculation, right? Remember, instead of 3, we're starting at 0.0. All right, so we're hovering around 0, it's normal. If it's the number is greater than 0, the tails are a little heavier. If the numbers are less than 0, that's a negative kurtosis, right? It's a little flatter. All right, so an example from our test score data set, our kurtosis score was 0.066. This is so close to 0 that I would say it was relatively normal. Okay, so just remember, a positive number, pointy, negative number, flat. Okay. Now you don't need to know this formula because the computer can calculate it for you. You can also pick it up what that means elsewhere, but this would be the formula for calculating the distributions. All right. So this is the mean of our data set score here minus the mean times 2. This is the sum of our sample size minus how many variables we have divided by our sample size. That's standard deviation. I let the computer calculate it for me now. All right, so a standard deviation quantifies how much an individual data point deviates from the mean. So if it's 3 standard deviations away from the mean, it's 3 major steps away from the mean. A low standard deviation means it's tightly clustered around the mean. So if it's within 1, it's close to the mean. A high standard deviation means it's more spread out. And if it's greater than 3, you have an outlier. Okay, so here's the empirical rule, so you can see these standard deviations, right? It states the first standard deviation indicates 68% of our data falls within the first standard deviation, either right below or right above the mean. So that means the probability of a score being pulled with 68% likely it's within the first standard deviation of a mean. 2 standard deviations means it's within 95% of the data. 3 is 99.7%. Almost all data will fall within 3 standard deviations from the mean. If it's above that, it's an extreme outlier. Okay, so why do we use the empirical rule? It helps us determine how typical or unusual a data point is in comparison to the data set. We can use it for quick comparisons between multiple different groups too. And it helps us identify outliers, which could be causing problems or indicate that we should check our data for accuracy. Now, what is a confidence interval? A confidence interval provides a range of values where we expect a population parameter, like the mean, to fall with a certain level of confidence. So I set my confidence level all the time for social sciences at 95%. You can pick it. A lot of times modern medicine uses 99%, but social sciences uses 95. Okay. The point estimate, this is the best guess for a population parameter, like the sample mean. A margin of error is how much variability exists in that estimate, because we're estimating it. We don't know for certain. And then our confidence level is the probability that the interval contains the true mean. So here's a look at it. We can look at this distribution here, this histogram. The red lines, that is the confidence interval between 82 and 92.4 from our sample data set. All right. So using a confidence interval of 95%, there's a 95% chance that any score we pull would fall in this area. Okay. So here's a quick reference of the key descriptive statistics that you would use and that we use throughout our presentation. Okay. And here, look, there's a confidence interval we just talked about, the estimated range where the true mean likely falls, right? Okay. And finally, here is a picture of the descriptive output I ordered from JASP, from the data set that I gave you an example on. Remember, a picture is worth 1,000 words. All of your statistics do not need to be presented in tables like this one. This is why we use graphs. We can glean a lot just from looking at a graph. We don't have to just look at tables. Okay. So how would you present your information? But look, we have 10 cases, none are missing, mean, median, and mode. They are not the same, but they were close. Our confidence interval, standard deviation, was 7.269. All right, our interquartile range was 7.75. Our variance was 52.84. Skewness, right? We had a slight positive skew of 0.106. Here's our kurtosis, which was also slightly positive at 0.06. I would say there was no kurtosis. Our range, we had a range of 25 scores with the minimum score, the lowest score being 75, the highest score being 100. And there's our quartiles. Okay. Okay. Reach out to me if you have any questions. Thank you so much for your time.